In this video, I'm going to introduce derivatives, and you're going to see that the definition involves limits. You're going to see that it's going to use the experience we've had dealing with piecewise linear functions. All right. So let's first write down the definition. The derivative is the instantaneous slope of a function. Okay, so what does that mean? Okay, you the limit of the slope around a point as the line segment gets smaller and smaller. So as I shrink the line segment around a point, the slope's going to approach something. The limit of what it's approaching, that's how we're going to define the derivative. All right. So an example is probably the best way to help this to make sense. So let's do this. Oh, and I should yeah, let's keep going. Calculate the derivative, in other words, the instantaneous slope of a parabola y equals x squared at x equal to 2. All right, so here we go. So let me first plot it, and parabola looks something like this, x squared, and so we want the slope of a line segment around x equal to 2. So let me put a dot here, and let me put another dot a little bit away from that, and let's say that that dot is at 2 plus h. Okay, so h is the x difference between those two dots. Okay, what is the difference in the y values? Well, let's first get the coordinates of both of those points. Okay, so the top one is at 2 plus h, comma f of 2 plus h. The bottom one is at 2, comma f of 2. Okay, so in other words, 2 plus h, comma 2 plus h squared, right? And then the other point is 2, comma 4. All right. Now, the reason I'm using h instead of a specific number is, imagine I have a knob where I can adjust h. I'm going to shrink h. I'm going to make h approach 0, and the goal is to figure out what the slope of the line segment between those 2 points is approaching. All right. So I hope you're still with me. So let me maybe use green to denote the line segment with the black dots as the endpoint. Okay, so there, it's that we want the slope of that green line segment I just drew. Okay, so that is, so the slope we know, m, is delta y over delta x. So in this case, it's delta y is 2 plus h squared minus 4. That's divided by 2 plus h minus 2. Okay, now let's do some algebra for a minute and simplify this. So let me expand out the 2 plus h squared on top. So that's 4 plus 4h plus h squared minus 4. The bottom simplifies to just h. And not only does the 2 and minus 2 cancel on the bottom, but on top the 4 and the minus 4 cancel. I can also divide out some h's, so I get 4 plus h. Okay, so that's the slope as a function of h. Okay, now let's take the limit. So imagine that I had you can probably already see because it's such a simple function, but imagine that I had a column and I was doing all this work to find the limit. So here's the h and the m. So if h was, and we want the limit of m, the limit as h approaches 0 of m. So that's the limit as h approaches 0 of 4 plus h. So if h was 0.1, then m would be 4.1. If h was 0.01, h would be 4.01. If h was 0.001, m would be 4.001. All right, and I think it's pretty clear that the slope is approaching 4. Okay, so the slope is approaching 4, so here's your first derivative. The derivative of x squared, the parabola x squared at x equal to 2 is 4. 4, we'll put a little box around it. Okay, so there you have it. There's your first example. Think about that one for a few seconds or a minute. You can pause the video, and then I will continue on a new whiteboard. All right, so let me now write the formal definition of a derivative using what I did here. Okay, so you're always going to have the same thing where you have that h, and you're going to do a lot of things similar. So in general, you'll have this: the derivative at x equal to a, the derivative of f of x at x equal to a is, okay, what we do is we take the limit as h approaches 0 of f of a plus h minus f of a divided by h. Okay. Look at the previous parabola example. Maybe do another one, thinking about what it means to take a slope and taking a limit, and you'll see that you always get something that agrees with this purple expression. All right, so let this be your guide. This is the derivative of a function at a specific value of x. Okay, where did this come from? This is just a fancy way to say that you're basically taking the slope of a line segment and you're shrinking the line segment and seeing what the slope is approaching. Okay, so that's why we had to learn limits before we could get here. Okay, so let's now do a example related to the parabola. Okay, how about this? Can we find the derivative of the parabola for all values of x? Okay, we found it for x equals to 2, but what about if we left the destination a variable so then we can adjust it? Okay, so for example, let's take the derivative at let's just use a. Okay, let's leave it as a function of a. So we're going to do the limit as h approaches 0 of f of x plus h minus f of x divided by h, and we're going to plug in, if you want to use a for x, then let's go ahead and let's replace or actually in my definition I used a, so let me go ahead and just use a and keep it a and not ever define a. Okay, where f of x is equal to x squared. Okay, so this is going to give the limit as h approaches 0 of a plus h squared minus a squared over h, and so that equals the limit as h approaches 0 of a squared plus 2ah minus a squared over h. The a squareds cancel, the h's cancel, and I also have a plus h squared that Let me put that plus h squared, and then the h's cancel with one of the h's in the h squared. So the whole thing reduces to the limit as h approaches 0 of 2a plus h. Okay, and that's equal to 2a. All right. So the derivative for any value of a is equal to 2a. Okay. If you say what is the derivative at x equal to 4, you multiply that by 2, and so you get the derivative is 8. If you say what is the derivative at x equal to minus 3, then you multiply that by 2, so the derivative is minus 6. All right, and etc., etc. Now, in general, for a value x, the derivative is 2x. All right, we say this. So what we've done is we've figured out the derivative for all values of x. That's a function. We denote the derivative function by notation related to f. Let me show you. Let me put a box around f, and the derivative function that we just found is, we write it as f prime x, and that's equal to 2x. Okay, so there you have it. We'll be doing this a lot. We'll be finding the derivative function for various functions. Now, what does that mean? That means that we're finding a derivative function that'll give us a derivative, in other words, the instantaneous slope for all values of x. All right. Okay, so we just did it for a quadratic. Now, we could run through the algebra for the following pattern as well. How about if I had a function 1 over x? Let's see if we could do that one. Okay, so we're going to do the limit as h approaches 0 of f of x, this time I'll use x instead of a, minus f of x divided by h. So that's going to be the limit as x approaches 0 of 1 over x plus h minus 1 over x over h. And let me switch colors, and let's multiply by the greatest common denominator, or excuse me, let me multiply by x times x plus h. So I'm just doing algebra. And then I'll multiply the bottom by x times x plus h. And okay, so there we have it. Now let's see if we can clean that up. So that gives the limit. On the top it simplifies to minus h. On the bottom it simplifies to h times, let me just distribute the x in, x squared plus hx. Now the h's cancel, so I get minus 1 over x squared plus hx. As h gets really small, that hx term gets smaller and smaller. So the limit is equal to minus 1 over x squared. Okay, so we say that if f of x is 1 over x, then the f prime of x, the derivative function, is minus 1 over x squared. All right, there's your second example. Okay. Let me write a few other patterns, and I'll leave it as an exercise for you to see if you can work through a similar development to get these other patterns. All right. So here I'll write here. I'll make a column. So a function and then the derivative for the derivative function. Okay. So if the function is if it's some arbitrary f of x, the derivative, we're going to call it f prime of x. Let's get that clear. If the function is x squared, we've already worked out that the derivative is 2x. If the function is 1 over x, we've worked out that the derivative is minus 1 over x squared. Okay. How would here's what I wanted you to work out. So what if I had a line? So what if the function was let's say mx plus b. Okay, you'll work that out and you'll see that the derivative is going to be the number m. That's a great example. Okay, the derivative is exactly what we get for the slope of a line. All right, and then see if you can work out this one too. Going back to the first row at the top, what if I multiplied a function by a constant? Okay, see if you can figure out why the old derivative, we multiply that by a constant to get the new derivative.